I got so.
Geoscience is a multidisciplinary field that relies on the synergy between physical observation and quantitative mathematical tools, specifically calculus, to model Earth dynamic system, while derivatives are utilized to analyze instantaneous rate of change, such as erosion speed or temperature gradient. Integration allows scientists to calculate accumulated total, such as groundwater volume or energy release. By applying this mathematical method, geoscientists can more accurately interpret geological phenomena, enabling better environmental management and the mitigation of natural hazards.
Hi everyone, today I will be presenting a mathematical analysis on coastal restoration at Pantai Cahayabulan, Kelantan. As we know, PCB faces critical erosion every year due to the northeast monsoon. High energy wave strip away the sand, threatening the shops and roads nearby. To save the beach, engineers use a method called beach nourishment, which simply means bringing in new sand to widen the coastline. But here's the problem. The beach doesn't erode evenly. Some parts are deeper than others. If we just assume the beach is a perfect rectangle, our calculation for the sand needed will be wrong. So my objective is to use calculus, specifically define an integration to calculate the exact total volume of sand required for a specific 50-meter sector of beach. Based on site data, the cross-sectional area of the sand needed isn't constant. It starts at 10 square meters and increases as we go further down the beach. We model this with the linear function. It x equal to 10 plus 0.5x, where x is the distance along the shore. To find the total volume V, we integrate this area function from 0 to 50 meters. We set up the integral of 10 plus 0.5x from 0 to 50. Using the power rule, 10 becomes 10x and 0.5x becomes 0.25x squared. When we substitute the upper limit of 50, we got 500 plus 625. This gives a final result of 1125 cubic meters. To make sure this is correct, I verify it using the trapezoidal rule formula. By treating the area as a trapezoid, I calculated volume geometrically, and the result was exactly 1125 cubic meters, confirming that our integration is accurate. So what does this number actually mean for the project? 1125 cubic meters is the sediment budget. Logistically, this tells us we need approximately 112 heavy-duty truckloads of sand just for this short stretch. This precise volume is critical for monsoon resilience. If we underestimate this volume, the new beach slope will be too shallow to break the monsoon wave, and the sand will wash away immediately. We also need to ensure the sand grain is coarse enough to withstand the currents. In conclusion, by applying the finite integration, we move beyond simple guesswork to a precise engineering solution. We determine that 1125 cubic meters of sand is the exact requirement to restore the sector of Pantai Cahayabulan, ensuring both financial efficiency and better protection against the next monsoon season. That's all from me. I will pass this to the next presenter. Thank you.
My name is Nadira Binti Harun with metric number E25A3649. Today I will be presenting my project title Integration, which is an analysis of groundwater storage capacity, mathematical modeling of the North Kelantan aquifer. Kelantan is unique in Malaysia because it relies heavily on groundwater, which meets 70% of its domestic demand. The North Kelantan aquifer is composed of quaternary sediment and acts as a vital natural reservoir, ensuring a stable water supply, especially during dry season. The problem is that traditional geometric approximation often fail to capture the natural curved shape of geological basin. To manage water resources Effectively, it is critical to estimate storage capacity accurately. Therefore, my objective is to use quadratic model to represent the aquifer cross-section and calculate its area and total volume using definite integration. Now, let's move to the core of the analysis. While a standard approach might integrate directly from negative 100 to 100, I have optimized the process by using symmetrical integration. Since the aquifer basin is symmetrical, I calculate the area from 0 to 100 and multiply it by 2 to cover both sides. The area A defined as 2 times the integral from 0 to 100 of the function negative 0.004 x squared plus 40 dx. After performing the integration, we get 2 times, open bracket, negative 0.004 x cubed over 3 plus 40x close bracket within the limit of 0 to 100. Next, I substitute the limit of 100 into the equation. 2 times, open parenthesis, negative 0.004, open parenthesis, 100 cubed, close parenthesis, over 3 plus 40 times 100, close parenthesis. This simplifies to 2 times, open parenthesis, negative 1333.33 plus 4000, close parenthesis. This finalized as 2 times, open parenthesis, 2666.67, close parenthesis, giving a total cross-sectional area of 5333.34 square meters. To estimate the total capacity, I use the formula volume equal area times length based on a length of 1000 meters. The total volume is 5,333,340 cubic meters. This is equivalent to approximately 5.33 billion liters. I would like to note that while a standard AI calculation might integrate from negative 100 to 100, but my method is much more efficient. By utilizing symmetry and starting from 0, the calculation becomes cleaner and reduces the risk of manual error. In conclusion, this mathematical model provides a more professional tool for geoscience water management. Thank you.
Assalamualaikum and hi, my name is Siti Normaisara and I will be presenting my geoscience case study titled Coastal Erosion at Kuala Nerus, Terengganu. Kuala Nerus is located on the east coast of Terengganu. This area is directly exposed to the northeast monsoon, which occurs every year between November and March. During this period, the coast experienced high energy waves and strong nearshore currents, which actively remove the sediments from the beach and nearshore zones. Over time, this monsoonal process caused the shoreline to gradually move landward, and the lost sediment is not fully restored during calmer seasons. The problem here is the actual rate of shoreline retreats over time has not been clearly quantified. Most existing studies focus on qualitative observations and lack a mathematical model that explains how fast the coastline is eroding. Next, we move to the mathematical formulation. So the shoreline distance was modeled as a function of t, which measure from a fixed reference point. Based on shoreline data, the shoreline distance was represented using a quadratic function, which is st equal to negative 0.02 t squared minus 0.3 t. For derivative calculation, to find rate of change of the shoreline, we calculate the derivatives of this function with respect to time. So by using the power rule, for the first term of this function, negative 0.02 t squared becomes negative 0.04 t. And for the second term, negative 0.3 t becomes negative 0.3. So by combining both terms, the derivative of the function of the shoreline function is s prime t equal to negative 0.04 t minus 0.3. After calculating the rate of shoreline retreat using derivatives, the results were verified using an alternative method known as central difference method. So the formula used is f prime x equal to f of x plus h minus f of x minus h divided by 2h. So for the rate at 2005, since 2005 is the specific year, I use the data from the 2000 and 2010, which is 5 years before and after 2005. Based on the Geoscience interpretation, the shoreline at Kuala Nerus has retreated continuously from the year 2000 until 2020. The erosion rate increased from 0.5 meters per year in 2005 to 1.1 meter per year in 2020. This shows that coastal erosion in this area has accelerated over time. In conclusion, this case study demonstrates how derivative can be effectively applied in geoscience to analyze real-world environmental problems.
Hi, my name is Margina and my part is about coastal erosion and Pantai Morik Selangor. In this video, I will show you how to use derivative to measure how fast the shoreline is retreating over time. Has experienced noticeable shoreline retreat due to natural process like wave action, tides and also monsoon season, as well as human activities such as coastal development. So understanding the rate of erosion helps planners protect the shoreline and manage land use effectively. We can model the shoreline distance from a fixed reference point such as a nearby road using the function steady erosion, which comes from the linear term minus the TT, which means every year the shoreline moves 30 meters closer inland. And this erosion rate is constant, while the curved line represents accelerating erosion come from the quadratic term minus 5t square. This means as time increase, erosion become more faster and the shoreline retreats more rapidly each year. The rate of shoreline erosion is the derivative of the function with respect to time, which ds over dt equal to 33 minus the 10t. So for student verification, use 4, which is mean 4 years, and substitute t equal to 4. The answer is minus 70 meters per year. So this means the shoreline is retreating at 70 meters per year at this time. So for geoscience interpretation, the negative value indicates the shoreline is moving landward, confirming coastal erosion. The increasing rate over time shows that the erosion is accelerating. So factors contributing include strong waves during monsoon and also rising sea levels and human activities like development along the coast. So in summary, derivative help us quantify coastal erosion. At Pantai Morik, the shoreline retreats faster each year, showing both steady and accelerating erosion. This mathematical and geoscience insight is important for effective coastal management and also protecting coastal communities. Thank you.
Lastly, I would like to talk about conclusion. What we learned about integration and derivative in geoscience. Integration in geoscience is understood as a way to quantify total physical quantity from models such as sediment volume for coastal restoration or groundwater storage in aquifer. By converting mathematical representation into real-world value, integration supports sustainable resource management, cost efficiency, and informed engineering decisions that can withstand environmental stress like monsoon season. While derivatives are understood as tools for analyzing how geoscience variables change over time or space, such as shoreline movement and erosion rate, they provide precise measurement of environmental change, reveal trends like accelerating erosion, and allow scientists to predict future conditions. Together, derivative and integration form a quantitative foundation that improve understanding of Earth system and support effective planning, mitigation, and sustainable geoscience practices.